I was thinking a little bit more about visualizing multiple linear regression. I want to show one more picture here. Remember that we're now in three-dimensional space. We can't represent things on a blackboard, on a whiteboard, or on a screen. We have to pull our data out into 3 dimensions. When we have 2 predictor variables, we have to think that we're no longer fitting a line, we're now fitting a plane. But the plane is still the model. We can still talk about that model, and there are still residuals or leftovers. What's important about multiple linear regression is that when we interpret the slopes, it allows us to say adjusting for or controlling for or holding constant the other variables that are in the model. Imagine that you're standing next to this big box right here. Here's you. I'm a really good artist. Here's you. And you're looking that way. You see how X is increasing? Do you see how when your X increases here, as this goes this way, you get a higher predictor of Z? Imagine that you were walking along this X variable, one step at a time. What's happening to Z? Well, as X increases, Z gets higher. I think we can visualize that from here. But what are we doing with respect to Y, this other variable? What that is doing is being held constant. We're going forward here, staying on this little line right here, and saying, how much does Z change every time I take a step, but staying in my own lane with respect to this other predictor? That's how multiple linear regression allows us to control for confounding. Now, spoiler, this is a pretty simple model. I shouldn't say simple. This model is not complex. There are only 2 predictors. We're going to add many more, and we're going to go into this crazy multi-dimensional hyperspace. But you can still visualize it here. Let's go back to the idea of predicting birth length from a baby's gestational age and its maternal age. And state it simple, we say regress, and then we have our outcome, Y, and then we might have our 2 predictors, X1 and X2. We still have residuals, leftovers. It's the distance from each point to the model, which is now a plane. And those residuals go into this calculation of the residual sum of squares. How much umbilical cord do you use to connect each baby to this surface? We also still have this idea of the total sum of squares. How much is each baby different from the mean of birth length? That's the total sum of squares. We take the sum for each individual baby, and we see how far they are from the mean, Y bar. Square those up, and that's the total sum of squares. We still can do the same thing to calculate what percent of the variability is explained by the model. There's about 1,200 units of total variability if we connected every baby to the mean, just a horizontal plane, a table in the middle of the room. We still have leftovers after we fit the model. And the difference between 1,262 and 685 is this, 577. And if we take that, how much the model explained, and divide it by how much total there was, we get this number, R squared. 45% of the variability in a baby's size can be explained by its gestational age and its maternal age. Now, we haven't talked about this yet, but there's also a statistic called an F statistic. And the F statistic says for a model like this, is the model better than just predicting the mean alone? And the answer here is yes. F, which we'll cover more when we actually do the test called ANOVA, F shows us that this model is better than no model at all, right? A model where you just have the mean. So when we fit this, remember, regress length on gestational age and maternal age, now we get stated as output for the model itself. And we can write out the model. We have the constant, or the so-called intercept. And then we have two slopes here. We have a slope for maternal age and a slope for gestational age. So the model gets written like this. Birth length equals intercept plus our first slope plus our second slope. And like we saw in simple linear regression, we can have null hypotheses and we can do hypothesis testing for these parameters. And we see that gestational age is still a significant predictor of birth length. That's a mistake, sorry. Of birth length after controlling for maternal age. And again, those p-values will tell us the same story around statistical significance as the confidence intervals. Look to see if the CIs include the null value of 0, and that'll tell you what the p-value is, whether it's significant. So this is now our multiple linear regression model, where we have one outcome and we have two predictor variables in the model. I told you at the end of the last set of slides that the most important part is how we interpret the slopes. The slopes are still, for every 1 unit increase in X, how much do we see Y change? This goes back again to 7th grade. Delta Y over delta X. Change in Y over change in X. Or rise over run. It's the same thing. But now our model is a little more complicated because we got two guys in it. We got two predictors in it. So we can interpret this output in one of two ways. For every 1 unit increase in gestational age, how does it change after controlling for maternal age? Or for every 1 unit increase in maternal age, how does it change after controlling for gestational age? Which one of these is right? Well, they're both right, but they answer different research questions. One research question is, how does maternal age affect the size of a baby? And I want to control for this important confounder known as gestational age. The other research question is, how does gestational age affect the size of the baby? And I want to control for the potential confounder of maternal age. It'd be like if you wanted to study, does diet affect diabetes? We sure as hell better control for exercise, because I know that's related to diet and it's an important predictor of diabetes. And if I want to say, does exercise affect diabetes? Well, I sure as hell better control for diet because it's blah, 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 confounding triangle and so on. So one person's confounder might be the other person's main exposure of interest, their bread and butter, so to speak. Let's look at an example of this. Here's a study about, does blood pressure predict cognitive performance? Continuous variable blood pressure. Continuous variable cognitive performance. This is a score called the global cognitive performance. How do we look at the relationship between two continuous variables? We can do a correlation and say, as blood pressure goes up, your cognitive performance changes. But anyone who has half a brain would say, well, how much? What's the strength of that relationship? And that's why we do regression, to look at the slope. So as your blood pressure increases, your cognitive performance goes down. And anyone who has 3/4 of a brain will be like, yeah, but maybe there are some potential confounders there. Maybe education is important. Maybe the more education you have, the better you are on global cognitive performance. But maybe the more education you have, it also kind of affects your blood pressure. Age might be important. Gender might be important. So what we see here is a really nice example of a multiple linear regression. And it's almost like they pulled this table right out of Stata or another statistical program. Here's blood pressure. Here's our slope, which is also known as the beta or the coefficient. That slope has a standard error associated with it. And that can be turned through a t-statistic into a p-value. And how do we interpret this slope? Pause the video for a second and see if you can write a one-sentence summary of that number, negative 0.003. You'd say for every 1 unit increase in blood pressure, your global cognitive performance goes down 0.003 points. Period? No, comma. After controlling for education, age, and gender. We also see that for this whole model, we get an R-squared value. 33% of the variability in your global cognitive performance can be explained by this model. Plug in your blood pressure, your gender, your age, and your education, and you can explain about a third of how people differ on this global cognitive performance. And the way they wrote this paper up, we see this in a multiple regression analysis that explained about a third of the variance or the variability in cognitive performance. And our main finding was that as blood pressure increases, your cognitive performance goes down. Now, you might have noticed something interesting on that last table. We'll revisit this in the next video.